Hey Global Impact students, this is Mr. Ellinger. This lesson is on two variable inequalities. Our learning target for the lesson is we want to be able to graph two variable inequalities. Some essential understanding for you from this lesson: the graph of a linear inequality contains all points on one side of a line and may or may not include the points on the line. Some background information for the lesson: while the steps involved in solving a linear inequality may seem straightforward, this knowledge opens the door to many advanced mathematical topics. The principles in this lesson will also apply to linear programming. Solving a linear programming problem consists of maximizing or minimizing a function subject to a list of constraints. Many economic, labor, and business problems can be solved using linear programming techniques. So graphing an inequality in two variables is similar to graphing a line. The graph of a linear inequality contains all points on one side of the line and may or may not include the points on the line. A linear inequality is an inequality in two variables whose graph is a region of the coordinate plane bounded by a line. This line is the boundary of the graph. The boundary separates the coordinate plane into two half-planes, one of which consists of solutions of the inequality. So here we have graphic. We have two different linear inequalities graphed. We have a boundary line, and we'll talk about what's the difference between a dashed boundary line and a solid boundary line. And when we graph these, we will have to shade part of our graph. The shaded part represents the solution set to the inequality. And we call those half planes. So our boundary line cuts the coordinate plane into two halves, one of which is our solution set, one of which is not. And the boundary line may or may not be a part of the solution set. To determine which half plane to shade, we're going to pick a test point that is not on the boundary. Check whether that point satisfies the inequality. If it does, shade the half plane that includes the test point. If not, shade the other half plane. The origin 0, 0 is usually an easy test point as long as it's not on the boundary. So again, use the origin unless the origin is on the boundary line. So what is the graph of each inequality? Well, in A, we have y is greater than 3x minus 1. So the first step is to graph the boundary line and use the equation form of this, y equals 3x minus 1. So this is 3x minus 1. We're going to use a dashed boundary line because the inequality is greater than, and the points on the line do not satisfy the inequality. So if it's just a greater than, just a less than, we have a dashed boundary line. Step 2, choose a test point. 0, 0. Substitute x equals 0 and y equals 0 into our inequality. We get a true statement. 0 is greater than negative 1, so we're going to shade the half plane that includes the origin. So here's the origin. Our boundary line runs just to the right of the origin, so this yellow area is our shading. Any single point that you pick in this shading will satisfy the inequality. Any single point that you pick over here in the non-shaded area will not satisfy the inequality, and that includes the boundary line. Okay, so just to give you an example here, 1, 2 is on the boundary line. If I substitute in 1, 2 into my inequality, we get 2 is greater than 2. Okay, and that is not a true statement. So that value cannot be in the shading. That's why we use the dashed line for this boundary in this case. So the boundary line, again, divides the plane up in half. We still have to have the boundary line even if it's not in the solution set. It's not in the shading, but it shows you the boundary of the shading. And now you can see if this were changed to a greater than or equal to, we would get a true statement, and then we would want to have a solid boundary line. All right, part B here. Y is less than or equal to 3x minus 1. The boundary line is, again, y equals 3x minus 1. So here is our boundary line. It's going to be solid this time because the inequality is less than or equal to, and you can refer back to the discussion that I had just a second ago. Shade the region opposite the region shaded above, okay, because now we're working with y is less than or equal to, but we can still check a test point. The origin 0, 0. If I plug in the origin into my inequality, I get a false statement. 0 is not less than or equal to negative 1, so we know that the origin should not be in the shading. Okay? Let's look at an absolute value inequality. What is the graph of 1 minus y less than the absolute value of x plus 2? So we know we have an absolute value inequality. We need to know where the boundary is. So we're going to treat this just as we would a linear inequality, even though this is absolute value. So the first thing that we'll do is we will isolate y. Once we have y isolated, and you can see here we have to pay special attention, we subtract 1 from both sides, so that gives us negative y is less than the absolute value of the quantity x plus 2 minus 1. We don't want negative y, so we have to divide through by a negative 1, or multiply both sides by a negative 1. When we do that, that reverses our inequality. That puts a negative in front of our absolute value, and then it changes the sign of our constant over here. So the graph of y equals negative absolute value of the quantity x plus 2 plus 1 is the graph of y equals absolute value of x reflected in the x-axis, okay, because of this negative here, translated left 2 units because of the plus 2, and up 1 unit because of the plus 1. Since the inequality is solved for y, and y is greater than, shade the region above the boundary. Okay, so when we have y isolated by itself on one side, this less than or greater than can tell us where are we going to shade. If it's y is less than, then we're going to shade below. If it's y greater than, we can shade above. So we can bypass the test point if we remember this. When in doubt, use a test point. But again, when y is isolated, we can refer to the inequality sign to tell us which side of the boundary line to shade. With absolute value inequalities, it's very obvious. With linear inequalities, sometimes it's not so obvious which is above or which is below. Okay, so what inequality does this graph represent? So here we have the graph of an absolute value inequality, as we see here. We see that the shading is above. We notice that the boundary line is dashed, so that tells us some clues about our equation or our inequality. Now we just have to figure out what exactly is the inequality. So the boundary line is the graph of the absolute value of the function y equals absolute value of x. It's translated though. So here's our parent function again, but the parent function has been translated. It's been translated, again, focus on the vertex. The parent function vertex is here. The vertex of our function is here. It's been translated to the right 3 units. It's been translated down 2 units. So a horizontal translation of 3 gives us absolute value of x minus 3, and a downward translation of 2, we know we need to subtract 2 from those absolute values. Okay, so our boundary is y equals absolute value of x minus 3 minus 2. The solution is shaded above the boundary, so the inequality is either greater than or equal to. Since the boundary is a dashed line, the correct inequality is a greater than. So we'll just take out the equal sign here, replace it with a greater than sign here, and we have our inequality. All right, folks, I hope you have a great day, and we will see you next time.